video and the next video I'll be explaining to you the intuition behind the decision tree classifier, how it works, and I'll give you an example to make sure that things are clear. We continue our frequency table based classifiers. We've done the first three and now we're doing the decision tree classifier. The decision tree classifier, what it does, as the name suggests, it builds classification or regression models, so it can be used actually for classification and regression in the form of a tree structure. So the name says it all. What it does, it breaks down a data set into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed. So we break down the data set into smaller sets with at the same time building or increasing a decision tree. The final result is a tree with decision nodes and leaf nodes. A decision node, for example, if you remember our weather data set, it can be the outlook. It can have two or more branches. For outlook, for example, we have 3 branches. We can branch on sunny, overcast, and rainy. For a leaf node, for example, to play or not to play, a leaf node represents a classification or a decision. So a leaf node, there's no branches, we only have a class or classes there. The topmost decision node in a tree, which corresponds to the best predictor, is called the root node. Decision trees can handle both categorical and numerical data. If you remember from before, if we need to transform, then we can use transformation techniques that we learned before in our data exploration and analysis tutorial. Now, for our data set, for our weather data set, if you remember, we had 4 attributes: outlook, temperature, humidity, and windy. All of them are of type categorical, and we had our target or our class to play golf, either yes or no. A decision tree might look like this. We can have a root node of our outlook, and then we branch for sunny, overcast, and rainy. And then for the sunny, maybe the best way to branch now is on windy. For true or false, we can have either yes or no. And for overcast, when overcast is in, then it's always a yes. We don't have any no's with outlook overcast. And then for rainy, after that we can probably split on or branch on humidity. Notice that temperature now is not used at all. We can branch on humidity. For high or normal, then we can have our leaf nodes now as having the class values either yes or no. Now the way it works, the core algorithm behind it is called the ID3 algorithm, invented by J.R. Quinlan. It employs a top-down greedy search through the space of possible branches with no backtracking. So it tries all possible branches and it chooses the best one. The ID3 algorithm, it uses entropy and information gain to construct a decision tree. Entropy from decision theory. Now the entropy, in case you're not familiar with it, is some sort of measure of uncertainty, and the value of the entropy is computed for example 2 or maybe 3 sort of classes or categories, and the way it's done is by multiplying the probability of each category or each class by the log to base 2 of the value of that probability and summing over all the values of classes. I'll come to that in the next slide. So a decision tree is built top down from a root node, and it involves partitioning the data into subsets that contain instances with similar values. So they need to be homogeneous. After we branch, things need to get more homogeneous. The ID3 algorithm uses entropy to calculate the homogeneity of a sample. So we use entropy to decide whether something is homogeneous or not. If the sample is completely homogeneous, the entropy is 0. So if all the values are the same of the same class, then the entropy will be 0. If the sample is equally divided, the entropy is 1. Now, as we mentioned before, the equation of the entropy is like this. It's the summation for all classes minus pi log to base 2 pi. Now pi is the probability of each of these classes from I equals 1 to C, the number of classes. Pi is the probability of that class times log to base 2 of that probability. The minus here is because log to base 2 of any probability is always between 0 and 1, and log to base 2 of any value between 0 and 1 is negative. That's why we have that minus sign there, so they cancel each other and becomes positive. If you look at this diagram here, we have probability here 0.1, 0.2, 0.3, 0.4 until 1, and here we have the values of the entropy 0.1, 0.2 until 1. Now for point here, for this point, at this point here, 0.5, we can have the entropy equals minus P log 2P minus Q log 2Q. Let's say P and Q are two values now at 0.5, so things are equally divided. And if we do that, the entropy is minus 0.5 log to base 2.5 minus 0.5 log to base 2.5, and that's 1. So if things are equally divided, then the entropy is 1. If everything is homogeneous, then the entropy will be 0, either there or there. The value of the entropy is 0. Now to construct a decision tree, we need to compute two types of entropy. We need to compute entropy of the target before splitting, and then we compute the entropy after splitting, and then we compute the difference between the two entropies and see the highest information gain. We'll come to that when we have an example, but just focus here that to build a decision tree, we need to calculate two types of entropy using frequency tables as follows. Let's assume now we have our weather data. The first type of entropy we want to compute is entropy of the target. So from the frequency table, now the equation for entropy of the target is entropy of S. S is our target now, summation of minus Pi log to base 2 Pi, and I is from 1 to C. So these are our classes. P of every class times log to base 2 of the probability of the same class, and we sum over all the classes. If we remember our weather data from here, our class now, we have 14 instances and we have 5 no's and 9 yeses. Now we compute the entropy now of our target, of our class, regardless of the attributes. And the frequency table for the class, for play golf, which is our target now, we have 9 yeses and 5 no's. Entropy of play golf is the entropy of 5 and 9, no and yes. Entropy of, because now the probability of 5 is 5 over 14, which is 0.36. Probability of 9 is 9 over, sorry, probability of yes. Probability of no is 5 over 14. Probability of yes is 9 over 14, which is 0.64. And we plug that in our equation. We sum over the values of the two classes of the yes and no. We plug in their probabilities, compute log to base 2 of that probability, and the value will be 0.94. That's an example for entropy of the target. The second one now is entropy using the frequency table of two attributes. Now if we split entropy, let's say for example we split using Outlook. Now focus on this frequency table for the Outlook now, and notice the counts now. We count them against we build the frequency table against the class values, and now we're only concerned about the rows. If you remember from before, from Bayesian classifier, we were concerned about the columns probability. This would have been 3 over 9, the sum of the yes and sum of no's. But now, because we want to use these categories of variable Outlook to split the data, then we're only concerned about the rows, about these categories, these values. So sunny, when the class is yes, the probability is 3 over 5, size 5 is the sum of the row, and when the class is no, probability is 2 over 5. Likewise for overcast, 4 over 4, 0 over 4. Remember the zero frequency problem from Bayesian classifier. The rainy is, when the class is yes, 2 over 5, when the class is no, is 3 over 5. And these now must sum up to 14, as you can see here, the number of instances. Now what we do is we compute the entropy for the target when we split by Outlook. And the way we do that is we have the probability now for the category or for the class times entropy of that category. Yes, so probability of that category times time entropy of that category over all values of the category, i.e. here our variable is outlook, so we do that over the three values for sunny, overcast and rainy. Probability of sunny times entropy of the values for sunny, i.e. 3 and 2, plus, because we have summation here, the probability of overcast times the entropy of 4 and 0, plus the probability of rainy times the entropy of 2 and 3. Now if we plug those guys in, probability of sunny is 5 over 14, probability of overcast is 4 over 14, probability of rainy is 5 over 14, and now the entropy of 3 and 2, we just use exactly the same concept as we mentioned here. We use the same idea here, minus p, the summation of minus p log to base 2p for each of them. And remember now, for example, for sunny, the probability of the yes is, the probability of the 3 is 3 over 5, and here is 2 over 5 when the class is no. So we don't use 3 over 9, and we're only concerned about the rows as we mentioned before. We plug those values in, that should be nice and easy, should be straightforward, and we end up with the value of the entropy as 0.693. After that, we need to compute the information gain. The information gain is based on the decrease in entropy after a data set is split on an attribute. So the information gain is entropy before splitting minus entropy after splitting. This is the entropy of the target as we mentioned before, and this is after we split using one of the attributes. Now, constructing a decision tree is all about finding attribute that returns the highest information gain, i.e. the most homogeneous branches. What that means is we want the one that gives us the lowest entropy, so the difference here is as high as possible. These things will make sense when we compute an example, but just remember that we need to compute two values or two types of entropy: entropy of the target or before splitting and entropy after splitting, and then we compute the difference. I'm going to stop here. In the next video I'll give you an example for things to make more sense. Thanks again for watching, and I'll see you next time.